Okay guys, welcome back. From in this video we will continue from the same place where we have left it in the previous video, that was about angle of twist. In this section we will develop a formula for determining the angle of twist, right? We already know that what is the relation between the shear stress and the torque, and on what factors does it depend. We have solved two examples on it as well. To generalize this development, we'll assume the shaft has a circular cross section. The first assumption is it has a circular cross section that can gradually vary. So the cross section is not constant, it is varying gradually along its length, right? So let me take you to the figure. You can see that the cross section is smaller over here and it's getting bigger when we are moving in this direction. Also, the material is assumed to be homogeneous and to behave in a linear elastic manner, right? As in the case of an axially loaded bar, we will neglect the localized deformations that occur at points of application of the torques and where the cross-section changes abruptly. Now, why we are taking this assumption that we will neglect the localized deformation? Because by Saint Venant's principle, these effects occur within small regions of the shaft's length, and generally they will have only a slight effect on the final result. Therefore, we will neglect these localized deformations, right? Now, using the method of sections, a differential disk of thickness dx located at position x is isolated from the shaft. Now, if you remember in the previous video, while we were uh, deriving the equation for the the shear stresses, we took a disk from the shaft. Again, in the same way, we will take this disk. If you can see, with the thickness of dx, it is at a distance x from this larger area of this shaft, and this disk is considered over here, which is subjected to an internal torque T of x, right? Its radius is c, and we are taking an element, this element, right? And this element is located at a distance rho from the center line, and the shear strain, it is experiencing the shear strain which is gamma. So I have explained these things, right? As a result, an element of material located in arbitrary radius rho within the disk will undergo a shear strain gamma. I already said that. The values of gamma and d phi are related by equation, namely, so this d phi, which is the angle of twist, right? This will be equal to gamma times dx, the thickness, divided by this distance rho at which this element is located, right? So this is basically an equation that is between the angle of twist, the shear strain, the location from the neutral axis or the longitudinal axis line, and the thickness, right? Now, since Hooke's law says that shear strain is equal to shear stress over modulus of rigidity, it applies, and the shear stress can be expressed in terms of the applied torque using the torsion formula. In the previous video, we have derived this formula that tau is equal to T rho divided by J. So we can put the value of tau in this equation. So gamma will be equal to T rho divided by J into G, right? Substituting this equation into the previous equation, the gamma in this equation, right? So d phi will be equal to the value of gamma into dx divided by rho. So the value of gamma is this, and we have put it the value of gamma, and here if you remember was a rho. The rho is in a nominator, and in the previous equation the rho is in denominator, so they both will cancel each out, right? And we will get this equation. Now if we integrate this over the entire length of the shaft, if we integrate it from here till here over the entire length L, and we can obtain the angle of twist for the entire shaft. So the phi, which is the angle of twist, is equal to integrating from 0 to L T of x dx, J of x, and G of x, where T is the internal torque, and it depends because as x is changing, torque will change, right? J of x will also be changing because of the x, and G of x will also be changing because of x, and dx is the thickness of this uh, small segment that we have taken, right? Now please note that we have to make it simple for its application. So this is the final form, and how we got this from this. So we have taken the torque constant, this torque is applied as a constant value. The cross sectional area is the constant. See, there is no variation in the area, just like this one. And we have applied it through entire length. So usually in engineering practice, the material is homogeneous. We have taken that the material, for example, it is steel, so G will be constant, right? So in terms of, instead of G of X, we will use G. Similarly, as a cross-sectional area is constant and external torque is constant, therefore Tx will be equal to T, J of X will be equal to J. So the equation will become phi is equal to TL divided by Jg. How L is here? Because we are integrating it over entire length, so dx will change into L. Now note that the similarities between this equation and the one we have derived for the axially loaded bar, and it was like this, where linear strain was equal to what? PL divided by AE. So please note the similarity between both the equations. L is same. Instead of torque, there was a axial load. Instead of polar moment of inertia, there was the area, normal area. And instead of modulus of rigidity, there was modulus of elasticity, but the purpose was same. It is area property, cross-sectional property, this is material property, and same is the here. Okay, so these are the similarities between them. Now one important thing is the sign convention. The best way to apply this equation is to use a sign convention for both the internal torque and the angle of twist of one end of the shaft with respect to the other end. So if we are taking this cross section at a distance x, now at this cross section, the segment, uh, the if the direction of your thumb is directing away from this segment, and then the torque will be positive and your fingers will curl in the direction of the torque, right? And vice versa. In this, for this segment, the away direction of the thumb is this, and the torque is the direction of the fingers, right? So these are the positive directions of the torque. And if it's opposite, for example, this direction, if it indicates the thumb is towards the segment, then the torque will be negative in the section, right? So this is the procedure, you can go through it for your information and knowledge. Let's go to the example 3. It says that determine the angle of twist of the end A of the A36 steel shaft. This is a steel shaft. This is point A, B, C, D. A torque of 80 is applied at A in the anti-clockwise direction, 150 at B in the clockwise direction, and 60 and 10 at C and D in the anti-clockwise direction. So three torques are in anti-clockwise and one is at the clockwise direction, which is at B. Each segment has different length, 3 meter, 2 meter, and 1.5 meter, right? Material properties are given. A36 steel is given. Now it says that what is the angle of twist of A? What is the angle of twist of A relative to C? So you have to find phi of A relative to C, right? The shaft has a diameter of 200 meter. It has a constant diameter which is 200 millimeter. Now solution. The first step is to find the internal torque, right? Because for the phi you need torque. So using the method of sections, we will take three different sections. For example, section 1 at here, section 2 at here, and section 3 at here. So when we take section 1, there is only one torque which is 80, right? Now the equilibrium says that if it is in the which direction, anti-clockwise direction, the torque acting here will be in the clockwise direction. Now curl your fingers in the clockwise direction and your thumb will indicate that it is away from the segment, so this will be positive, right? So TAB is positive and BC and CD are negative because they are vice versa in the opposite directions, right? So these results are also shown on the torque diagram. This is the torque diagram where 80 kilonewton meter torque is applied in section AB. In the section BC it's minus 70 and in section CD it's minus 10, which indicates how the internal torque varies, right? So now we are done with the torque and we will find J, which is very simple, pi by 2 into radius power 4, and then we will put in the equation of phi. This is our equation, right? So we are given with the T, we know L, we know G, and we have find the J. So we found the T right in all the sections. We found J. G for A36 steel is 75 gigapascal, right? Therefore, we know all the variables now. Phi A, if please keep in mind that we were in the question we were required to find out phi A over C, right? It says angle of twist of A relative to C. So actually they are asking about this, but we are solving this as well for your information that okay, if it says that find the angle of twist at A, then how you will find? So you have just to sum up the value for all the three segments. This is segment AB, BC and CD. See, in AB 80 kilonewton positive, in BC 70 negative, and in CD 10 negative, and their lengths are also different. So please check the values: 80 positive, 70 negative, and 10 negative, and 3 meter, 2 meter, and 1.5 meter. Of course, J and G will remain constant because the material is same and the cross section is same. So twist at A is 7.22 into 10 power minus 3 radians. Now the required is to find the A with respect to C. So we will remove the segment CD and we will only consider segment AB and BC. So solving both, we will get phi A with respect to C is equal to 8.49 into 10 power minus 3 radians, right? Both results are positive, which means that and A will rotate as indicated by the curl of the right hand fingers when the thumb is directed away from the shaft. So the thumb will be away from the shaft in this direction at A, and it will be curling in this direction, right? This was our example 3. Now the example 4 says that please first consider this figure. There are different gears attached with this shaft. At point A is a gear, C is the gear, D is the gear, right? And E is the support, B is also a sort of support. The lengths are given 0.4, 0.3 and 0.5 meters. The gears attached to a fixed end steel shaft, this is a fixed end steel shaft, are subjected to torques 150, 280, 40. This is anti-clockwise, both of them are clockwise. If the shaft has a dia of 14, this shaft has a dia of 14 millimeter, determine the displacement of tooth P. The gear at A has teeth, and it says that the teeth P on this gear A, you have to find its displacement. So to find the displacement, you have to find the angle of twist, right? G is also given. So in the same manner as we determined it for the previous case, that take the sections, the first section will be here, second section will be here, and third section will be here. So TAC will be equal to 150, TCD will be equal to 150 minus 280, and it will be minus 130, and TDE will be equal to 150 minus 280 minus 40, and it is minus 170. So all three are given here. The second step is of course again the polar moment of inertia, and it is again the same, the values here. And the third and last step is to find the phi A. Now phi A is equal to TL by JG. Again there are three segments AC, CD and DE, and we know the value of T for all of them. We know J, we know G, and we also know the L. L is 0.4, 0.3 and 0.5. So putting these values, we will get phi A is equal to minus 0.2121 radians. So that value is negative. Since the answer is negative, so by the right hand rule, the thumb is directed toward the support E. Okay, so here it will be directing towards support like this direction. Okay, and therefore gear A will rotate as shown in figure 14C. It will rotate in this direction and not in the direction of the applied torque, because the resultant torque is in this direction. The displacement of tooth P. Now what was required? The displacement of the tooth P. So we note the angle of twist of A, which is phi A, and now we just need to multiply it with the radius, and radius is also given, which is 100 millimeter. So the displacement of tooth P on the gear A is 21.2 millimeter. All right. So this was all about the determining the angle of twist, and now we will very briefly discuss the torque in the solid non-circular shafts. Since it was demonstrated previously that when a torque is applied to a shaft having a circular cross section, that is axis symmetric sections, the shear strains vary linearly from zero at its center to a maximum at its outer surface. Let me take you here, right? Here we discuss that it will be zero at the center and it will be maximum at the outer surface. So furthermore, due to uniformity, the cross section do not deform but rather remain plane after the shaft was twisted. So the circular section doesn't deform and it remained plane. But shafts that have a non-circular cross section, for example, this rectangular or square section, are not axis symmetric, and so their cross sections will bulge or warp when the shaft is twisted, right? So when it is twisted, see what is happened to these squares, these all warped. So because of this deformation, the torsional analysis of non-circular shafts becomes considerably more complicated and will not be discussed in this text, right? At this level, we cannot find out the formulas and the methods because they are too complicated. So simply using the theory of elasticity, the table I have provided provides the results of the analysis for square cross section, right? Along with those for shafts having triangular and elliptical cross sections. So in all cases, if you see these dots provides you what? The maximum shear stress occurs at a point on the edge. It is on the edge and not at the corner. Why? Because the edge is the most nearest part to the center, right? And that is closest to the center axis of the shaft. So either it is a triangle, square, or ellipse. The most near part, the edge, the point on the edge that is most near to the center will gives you the maximum stress. Also given are formulas for the angle of twist for each shaft, and the angle of twist formulas are also given for these shafts, right? So what you can do is just simply, if for given data tau max is equal to 4.81 t by a cube, you know a, right? So you can find t or you can find tau max, and once you find t, then you can find phi as well. So these are all similar, just like these four examples, and please do your homework and calculate the stresses considering this shaft as a rectangular and sorry, not rectangular, a square and triangular as well, and solve all these four examples, and you will better get good ideas of how it works and how it behaves. So thank you very much for now.